Going to dive into a number of specific topics in a sequence here. Just hit a bunch of them at once. These are areas where mathematicians know better than you. Sorry, I know you don't like hearing that, but it's true. Um, and in particular, there are cases where I was saying the right answer, talking to people who went to an academic institution and heard the simple answer. And because they went to an academic institution to hear the simple answer, they thought they knew better than me. It's really embarrassing. One of them happened when I was in high school. Backstory on this: a few hundred years earlier, Leibniz, he was developing the calculus. Newton stole it from him, and so he was looking at how to prove the principles of the calculus using what he called infinitesimals, infinitely small things, as if they're real. But today, when you take math classes in school, they will tell you that 0.99999 repeating is equal to 1. And they use this cute little argument to show you that it's definitely 1. Leibniz did not agree. He said that 0.000000 with a 1 infinitely far away at the end, you put a 1 at the end, that's an infinitesimal. And so zero point 0.9 repeating and 1 aren't the same. They differ by an infinitesimal. And he was using the calculus on that principle. He was developing all of our calculus under the assumption that there was this thing called an infinitesimal. And kind of like the Dr. Seuss book Horton Hears a Who, he assumed that the infinitesimals behave just like normal numbers do, but infinitely smaller. And that there was a world of countable infinities that all behave just like the normal numbers do. You got real numbers, the countable infinities are the same. So he was operating under that principle. And then they found a paradox. This is a while later they realized there was a paradox with that treatment of number. And so they threw it away. They threw away the infinitesimal, and they're like, oh gosh, how do we deal with infinity? And they were freaking out for a while. They're like, what do we do? And this crazy guy, actually institutionalized, named Cantor came along. And he started making arguments about what infinity is really like. And so he created this hierarchy of infinities. And we're still arguing about which infinity is where and things like that. But there's this whole hierarchy of infinities. And that's Cantor's infinitudes. And we now argue that there's no such thing as an infinitesimal. But that duality between the Leibnizian frame and the Cantorian frame are parallel to Euclidean and non-Euclidean geometry. In Euclidean geometry, two parallel lines never meet by definition. We defined it that they stay equidistant. And so, of course, they can't meet. And then non-Euclidean geometry says, well, what if they meet at infinity? You know, you try to take induction on real numbers to infinity. There's a question of how does induction apply at infinity? And this is where the dualities in mathematics appear, is how do you apply induction at infinity? So we have Euclidean and non-Euclidean geometries, and we have Cantorian and Leibnizian infinitudes. And so I was trying to explain to math teachers when I was in high school that the Leibnizian frame is equally valid from a combinatorial argument. If I have a bucket and I can put one marble in that bucket, and I have 10 different colored marbles to choose from, I have an infinite number of each color. The first marble has a 0 on it, the second marble has a 1, 2, 3, 4, 5, 6, 7, 8, 9. There's 10 marble colors. I can only put one marble in this bucket. Then there are 10 different ways that I could put a marble in the bucket. If I have two buckets, now there's 10 times 10. There's 100 different ways to put marbles in these buckets. As I get more buckets, the number of ways that I can put marbles in those buckets is multiplied by 10 each time I add another bucket. Okay, now we're going to have an unbounded number of buckets. There's no end point to the number of buckets. That is a countable infinity. And here's the problem. What if I put a decimal point somewhere? Does that change things? Does that change the combinatorics of how these buckets, numbers of combinations? No. No. So if I put a decimal point and then I have a string of buckets and I can put 0 through 9 in each bucket, that's the same size set as if I put a decimal point on the other side. They're the same kind of infinity. And the problem that y'all had been running into is the same categorical error that was made by the ancient Greeks when they claimed that there was no such thing as a negative number because of the way that they defined the metric. When they wanted to measure the number of something, they measured it as length. They thought of number as ratio. And so you had a measure and you'd measure it and it's positive. And you had another measure and you'd measure it and it's positive. So they had a big argument about how you can't have a negative measure. You can't unmeasure to less than nothing. Your measurement gets down to 0 and there's no way to be negative. So the way they framed the question prevented them from admitting that negative numbers can exist. Until accountants started charging them debt. Accountants with debt, they're happy to have negative numbers because you owe me. So it's that way of constructing a metric that limits your ability to talk about mathematical number. And so that was the problem with the Cantorian frame versus the Leibnizian frame. When you have a system where you allow an infinitely long series of digits after a decimal point, then you must also allow an infinite series of digits before the decimal point. Just like positive and negative numbers. And that gives you both the infinitesimal and countable infinities, just like Leibniz said. So one of my classmates, her dad was a physicist at Livermore Labs, and he carpooled with a mathematician at Livermore Labs. And I talked to her, and I'm like, can I talk to the mathematician? So I wrote a letter. She gave it to her dad, who gave it to the mathematician in the carpool. He wrote me back with a bunch of circular arguments. This was embarrassing. I was like, wow, the mathematician at Livermore Labs is using circular reasoning, where he was pointing to mathematical theorems that disproved what I was saying. And I had to explain to him that those theorems were derived from Cantor. So he was taking Cantor as his starting assumption to derive a set of theorems, and then using the theorems derived from Cantor to prove that Cantor's right. That's called begging the question. That's what that fallacy is. So I had to explain this to him a number of times. We went back and forth a few letters. He consistently only used circular reasoning. And then he gave up. He got very angry that I kept pointing out that he was using circular reasoning. So it wasn't until a number of years later that I heard about Abram Robinson, I think was his name. Back in the 60s and 70s, he was working on the original arguments that proved that the Leibnizian infinities had a paradox. And he showed that it wasn't actually a paradox. They'd made a mistake. The Leibnizian frame of mind is not paradoxical. It is self-consistent. It is coherent. And so we can't invalidate it. It is an equally valid way of considering number. And that's called non-standard analysis. And I was right. So let's look at another example. When I was in middle school, I was trying to explain to other kids in middle school that the rules of entropy mean that you can't undo entropy. You can't reduce entropy, but you could stay constant, technically, which would be perpetual motion. And Jacob in particular, I won't say his last name for his sake, he spent the next 2 years pointing and laughing at me every time he saw me at school, saying, "You think perpetual motion's real? Ha ha ha, you don't understand." And I'd shrug, because he didn't understand the math. And it was back in the early aughts that there was a physicist who wrote up a paper where he hypothesized that we might actually be able to form a perpetual motion machine. This doesn't mean you get infinite energy. That's a totally different idea. This is just a machine that you start it running, and then it will keep running on its own until you break it or stop it somehow. You have to stop it for it to stop running. It'll keep running without ever running down. And so he wrote that paper, and predictably, the entire physics community laughed in his face. They said, that's ridiculous. You can't have perpetual motion. And so then a number of years later, he did it. He made a perpetual motion machine. It worked. Other physicists heard about that, and they're like, oh, I want to try. And they made it, and it worked. And this is classic physicists, because they're usually narcissistic. They didn't want to admit that they were wrong. So they didn't call it a perpetual motion machine. Even though one of the physicists who were working on quantum entangling two of these perpetual motion machines, they got interviewed by a science journalist. The science journalist was asking the physicist a question, and the physicist admits, and this is verbatim from the interview, he said, perpetual motion is real as long as you keep your eyes closed. It's a quantum effect. As soon as you observe it, you disrupt the system, and that causes the machine to break. You just broke the machine. That's why it stopped running. So those perpetual motion devices are now used as an instrument to test when observation has occurred. They have a real function. You're not extracting infinite energy, but you can use them as an instrument. And physicists didn't want to admit that they were wrong about perpetual motion, so they called it a time crystal. That's a time crystal. It has a heartbeat until you observe it. And the heartbeat doesn't stop on its own. It's perpetual motion. And there's this other concept I mentioned in my other video about entropy. Physicists and engineers concern themselves with work in a system, which is not the total energy in the system, because there's lots of energy from heat, but it's how much of a difference between places. If there's a disparity in energy, then you can extract work energy from the system by moving some of the energy from one side to the place where there's not as much energy. And the assumption is that you're going to run out. You're going to run out of work, because eventually you've moved all the energy equally. And now once it's as hot in the engine as it is outside on a summer day, the engine stops working. You don't have a temperature difference anymore. You can't get the engine to run. But there's a problem with that, because physicists also tell you that the universe is expanding. And if you got all this heat right here, and then the universe around it is getting bigger and bigger, then there's more places to put that heat. So you're not ever going to run out of work. Now, the machine that you use to extract that work, eventually it'll be the size of galaxies, where you're letting a galaxy fall toward another galaxy and then fly past in an elliptical orbit. And as it flies away, the universe expanded between them. The space itself got wider while the galaxy was on its elliptic path. And then when it falls back toward the other galaxy, it's traveling on a longer path, so it builds up more acceleration. Stuff like that. It's going to be a very big machine. And it's very hard to extract energy from that, maybe from the torque induced, something like that. But yeah, you're never going to run out of work in an expanding universe, by definition. They just didn't think it through. Here's another problem that I keep trying to explain to people, and they laugh in my face, and they never learned the details, so it's kind of funny. In physics, the fundamental argument is that all forces are mediated by particles. That's why they got like gravity particles and stuff. They have to say that, oh, these two subatomic particles are glued together. Why? Because of gluons. Gluons are bouncing between them and gluing them together. So you can't just have a energetic effect unless you have a particle mediating it. But there's one particular thing in physics that they never bothered to say what the particle was. They happily accept that it happens. It's happening everywhere, and yet there's no particle. Wave function collapse. Like if you look at a Feynman diagram, there's supposed to be virtual electrons going in every direction, virtual photons taking every path. There's tachyonic electrons where they're traveling fast in the speed of light in every possible orientation. And then they disappear. What made them disappear? What particle interaction got rid of those? So that's something you might want to work on that before you tell me you understand physics. And similarly, there's this long-standing argument, which we only recently started admitting we should probably fix. Physicists are like, yeah, let's look at some alternatives to actually like fix that problem. Quantum mechanics says things that don't match up with general relativity. They are incompatible. Either one of them is wrong, or they're both wrong. Those are the only options. They can't both be correct. Okay, so people are starting to look at like Mond and like quantum gravity and all these alternatives. But the problem is they're trying to pick which one is right and build on it. And that's a mistake. Because we know that the universe is not at the scale of subatomic particles. The actual pixels of the universe, the pixels of space-time, are done at the Planck scale, which is a lot smaller. And anytime you got a system where there's small stuff with certain dynamics, and then you see patterns at the big stuff, the pattern at the big size is not what was happening at the small size. It's just the emergence of the small size dynamics. So when we have rules for chess pieces, again, the chess pieces have certain rules, but then the game of chess has other patterns that appear as a result, as an emergence of a higher level of order. And it's basically the same with subatomic particles. The Planck scale's got some weird stuff going on. We can't see it. We can't build a particle accelerator that powerful. And then that interaction builds in complexity until it simplifies again. You have an accumulation of complexity as you get more particles until it collapses into a simple form. Again, that collapse is interesting. Why does complexity collapse into simplicity again? And so the collapse into simplicity happens at the scale of subatomic particles, and that's when we see symmetries arise. And you can argue about whether it's Garrett-Lisi's E12 symmetry or Cole-Fury's Octonian symmetry. But those are the symmetries observed at the scale of subatomic particles, not at the Planck scale. And what we see over and over again is that even if the Planck scale was complex and messy and chaotic, there will be a layer above it somewhere, higher above it, where we see emergent patterns. The same thing happens with stuff like your heartbeat. Your heartbeat is beating pretty regularly, but the signals from your brain to make your heartbeat are a chaotic mess. And it's an emergent property of the system that leads to a steady heartbeat. Same thing for your sleep cycle, your circadian rhythm. When researchers were shocking bright lights at mosquitoes, like surprising them with bright light, it disrupted their circadian rhythm. Their signal's chaotic, and it was leading to a steady day-night sleep cycle. Once they disrupted that, the mosquitoes were waking up and falling asleep at every random hour. It was a completely chaotic result. So we know that even if you have weird stuff down here, it's probably eventually going to create a pattern when you get a big bunch of them together. And what I was arguing when I was 12, and I was very happy to read Stephen Wolfram's New Kind of Science when that arrived. When that got published, I was like, hey, he's saying the same thing as me. I was probably the only person happy to read Stephen Wolfram's New Kind of Science. And then I also published an essay a few years ago, the week after Stephen Wolfram talked about his constructor method for a mesh of space-time. I read his whole work that week, and I wrote an essay pointing out some of the problems. So I was saying when I was 12 that the most plausible explanation, the hypothesis that would most likely be true, naively, is that the Planck scale is constructed as a web of theorem. That you start out with an axiomatic set. That's at the beginning of time. And then derived from that axiomatic set are a set of theorems. And that's moving outward in space and time. And as you build theorems upon theorems, you're getting an expanding mesh. And we can take time-like curved slices for different observers through that mesh. And that would form the appearance of particle dynamics on that surface that we sliced. And so I assumed back then that the axiomatic set was probably pretty simple. I don't think so anymore. I think it's a very complex axiomatic set that's generating a complex web of theorems. Because you can have one theorem over here and one theorem over here, and they combine to a theorem in a different part of the mesh. So there's lots of skip connections, basically. But even that chaotic soup, when you get enough of it, it's going to emerge as a pattern of order, and you're going to be able to find symmetries in that pattern of the higher level. So that's one of the other areas that I've had a bone to pick, and people usually laugh at me, even when they think they're educated, without understanding the real reasoning behind it. And this goes to a crux, the core point, which is scientism. Scientism is the magical thinking where people hold scientists and scientific discoveries on a pedestal like a priest who has direct communion with God, and they presume that science dogma must be the truth. And then they go around propagandizing that scientific dogma. Gotta let you know, there's a big difference between science and mathematics. Science is based upon a set of observations using the limitations of instrumentation and hypothesis formation within the real physical world, while mathematics is a place where you get to test the theorems which would be true if certain axioms were true. So a mathematician gets to say, I'm going to assume these truths, not because I think they're actually true. I'm just going to assume them to see what would be true if these axioms were true. And that structure in mathematics is why mathematics can be perfectly, definitely correct. When we say that something would be true if the axioms are true, that statement as a whole is definitely true. But when scientists try to say that they have correctly described this universe, you got to be careful. So when a mathematician proves something, almost certainly they are actually right. But when a scientist thinks they've proved something, you can wait 250 years and people will realize that they were wrong most of the time. So if we jump ahead to 250 years from now, we're going to look back at the textbooks today and we're going to say, that's wrong, that's wrong, that's wrong, that's wrong. Almost all the science that they tell you today is wrong. It's just an approximation of reality. And there's an error that allows that to happen, where scientists become enamored of mathematicians' ability to write an equation, a formula. And so a scientist will take a set of data and they'll find a function, a mathematical formula that fits that data. And then the scientist will think that the formula is the real rule that reality is following. Mathematicians will tell you, you can construct an infinite set of different formula that all fit that data. And each of those different mathematical formula that fit the data you observed, they're all going to have different conclusions for the domains outside of your data. They're all going to lead to different assumptions about what happens in the areas you haven't observed. So Karl Popper, a century ago, was a philosopher who correctly pointed out that science doesn't have the power to find truth. Science can never find truth. You're just going to have to give up on that fantasy. The only thing that science can do is disprove a hypothesis. And categorically, Sherlock was wrong. If you have four hypotheses and you disprove three of them, that does not conclude that the fourth hypothesis is correct. Because there might have been a fifth hypothesis you never thought of, or a sixth or seventh or eighth, and they're probably much more complex and nuanced based on understandings you don't even have yet, data you've never even seen. So because science is only viewing a small slice of the universe, the part that it can measure, and because they're only coming up with hypotheses that they can understand, they cannot exclude three hypotheses to conclude the fourth. That's not within their power. Science can only disprove a hypothesis. Science can never find any truth.